cry in the corner later. No, I'm just kidding. All right, so if we were going to simplify this, what would we do? Oh, sorry, Matt. I didn't know if you were like for sure. Yeah. Okay, so if we have an equation, like there's an equal sign and something on the other side, we can multiply through by x to eliminate the denominator. We don't have an equation here. We only have an expression. Okay. Okay, so basically we rewrite it so that they have a common denominator, right? So our 1 is like x over x. And so then this expression is x plus 3 over x. That's as simple as it gets. No, those x's do not cancel, okay? Because the one is plus a 3 and the other one isn't. Is this okay with everybody? So then we want to be able to do that same thing with this, okay? And so we might be thinking, how do we do that? So one of the things that we're going to do is we want to think about how to replace things with stuff that they are equal to. Okay, so this is why I have this list of identities up at the top. And basically, what you're going to be doing throughout this chapter is two things. You're going to be simplifying or proving things are true, but the simplifying skill is kind of the same as the proving they are true because you kind of plug stuff in and do the same idea. Or you're going to be solving some equations. Those are the two main things that we're going to do. The thing is, to simplify or prove that two things are true, that requires us to have some tools. Like here, we had to know that 1 could be rewritten this different way. We just happen to know that from our algebra experience and from other math experience. If we're going to do it with stuff that has trig in it, then we have to remember all the different ways we can rewrite certain trig values. So for example, the cotangent is the reciprocal of tangent. So one way to rewrite the cotangent is to say, that it's 1 over the tangent, right? Fair enough? All right, so what's another way to rewrite secant? 1 over cosine. Now, I am not saying that every time you see secant, you're going to write it as 1 over cosine. This is where the critical thinking part comes in. You have to make decisions about how you want to actually rewrite something or if you want to actually rewrite it. But we want to remember all of our options. So then the cosecant is 1 over the sine. Okay? Yeah. Alex. What's that? Cotangent. What's the problem?
I thought it was like a list, like cotangent and secant.
Oh, I didn't put sine and cosine up there on purpose. So I'm not listing like sine. I'm listing ways we can rewrite things. So there's not really a way for us to rewrite the sine. The sine is the sine. Now, technically, you could rewrite the sine as 1 over the cosecant if you wanted. Okay. So I just listed the reciprocal functions. Does that make sense? And I'm reminding you that this is a reciprocal function, which means you could rewrite it this way. Okay? Now, the tangent, what's another way that we could write the tangent? Helen? Good. Sine over cosine. Now, we think like y over x because we were trying to relate before our unit circle to our coordinate plane. But now we're just thinking of ways to use some trig functions to rewrite other trig functions. So we're trying to keep it in the realm of like sine, cosine, tangent, that kind of stuff. So the tangent is sine over cosine. Then what is yet another way to write the cotangent besides 1 over tangent? Eric? Good. Cosine over sine. So again, the purpose of having these here at the beginning was just to remind you about what these mean, but that their meaning then means they could be written a different way if you wanted to use them in a context to make them look different in order to simplify something. And this is a big example of that. 1 can look a lot of different ways. We made it look like this so that x was the common denominator, and then we could actually simplify. So this kind of substituting it for something that means the same thing but looks a little different will help us change or simplify things. Okay? All right, now, the sine squared plus cosine squared part of it is going to be a little bit different here because we're actually going to prove one of our identities, or at least show, maybe not a proof, but showing that it actually works. So how did we find sine? What did we say on the xy radius world? So like if you found an angle on a circle, oh, here's my angle location. We said the sine of that angle was equal to what? Good, y over r. So, And then notice it's squared. So if I squared this fraction, the y would end up squared, and so would the r. Okay. All right, and then how did we express cosine? Good, x over r. And again, notice that it's squared, so this would be x squared over r squared. Those already have a nice common denominator, like we were aiming for right here. So we can combine this together as one fraction that says y squared plus x squared over r squared. And then I want you to remember that with those ratios, you should think about your unit circle, okay? The way we got these ratios was x was representing a distance here in the triangle, y was representing a distance here, and r was representing a distance here, okay? And this is a right triangle. Okay? If we use the Pythagorean theorem, what relationship do we get with x, y, and r? What would it say? R squared equals x squared plus y squared. Notice what you have in the numerator right here. Okay. And according to this calculation, x squared plus y squared should equal what? R squared. So is it okay with everybody? I'm going to substitute out the x squared plus y squared because I know it's equal to r squared, which is then going to make this fraction look like r squared over r squared. And what would that be equal to? 1. So sine squared of an angle plus cosine squared of an angle is really going to be equal to 1. Interesting. Okay? So this is actually the first identity that we're going to work with. So these are some identities or some things we know about trig functions, and we actually knew all of this stuff already. This was just a reminder that when you see this now, you could rewrite it like that if it's more useful. And now we're going to start coming up with these identities that we might not have seen before. And today they're all going to focus on things we call Pythagorean identities. Pythagorean because they all come from this idea. Helen? No. Good question, though. So her question is really common and actually creates a lot of error when we're doing stuff. So her question is in regards to this. If the sine squared plus the cosine squared equals 1, does the sine plus the cosine equal 1? And my answer was what? No. Why is this not true just because this one is? Shannon? Okay, good. So it would be like y plus x over r squared, okay, or over r, and that's not going to equal the same thing. Like x plus y doesn't equal r. Only x squared plus y squared equals r. And on this, if you thought, well, if you take the square root of both sides, not really. If I take the square root of this side, yeah, I get 1. When I take the square root of this side, do I get sine plus cosine? No, it's all packaged in there, right? It kind of goes back to the Pythagorean theorem idea that 3 squared plus 4 squared ends up equaling 5 squared, right? I know that because 3, 4, 5 is a Pythagorean triple. Okay, so 9 plus 16 equals 25. But does 3 plus 4 equal 5? No. Okay? Is that all right? Okay, so that's because if we take the square root of both sides, when these are being added together, that sum is happening before the radical here, and we can't just separate those underneath there. If they were multiplying each other, it'd be a different story. Okay? All right, good question. All right, so what we're going to do is we're going to list the Pythagorean identities. So you see a box on your paper that looks like this. So the first thing I want you to do is in this first box, we're going to put the identity that we just came up with. So like sine squared theta plus cosine squared theta equals 1. Now, we're actually going to write this a couple different ways. And then once you see it, you'll get used to it more often. But if sine squared plus cosine squared theta equals 1, can somebody rearrange this and tell me another rule that's true? Julia?
1 minus sine squared.
Good. So 1 minus sine squared theta equals cosine squared theta. Do you guys see how this is the same as this? She's just moved something from one side to the other. So what's another version of this that we could write? Helen?
1 minus
Good. Now, as we do more and more of these problems, our job is to become like master manipulators. We want to take something and we want to manipulate it and change it. without breaking any mathematical rules to make it look the way we want it to look. And sometimes it's to simplify, sometimes it's to solve, and sometimes it's because someone said verify that this is actually equal to this other weird looking thing, and we have to just like manipulate it till we can get it to look like that. Okay? So here we see this written 3 different ways to kind of open our eyes at the beginning of this journey of like, oh yeah, like it could be like that. That's really the same. That's really the same. But once we've seen this, we just have to kind of keep an open mind that every formula we get, we could obviously rearrange many different ways if it had different pieces like that. Okay? All right. Now what we're going to do is we're going to take these formulas and we're going to manipulate them a little bit more. So I have this. You don't have to write this part down if you don't want to. You can. There are several ways. We're going to do a proof in a minute. Right now we're not going to do a proof, but I'm just going to talk about manipulation. So I can take an equation, and as long as I divide both sides by an equal amount, I can divide both sides by whatever I'd like, right? And it remains equal. Okay? All right, so I'm going to choose to divide both sides of my equation by sine squared theta. Okay? So this side I'm going to divide by sine squared theta, and this side I'm going to divide by sine squared theta. What happens on the left side of my equation? Nothing? I can rewrite this. So this is the denominator now of both of these. What's sine squared over sine squared? 1. Plus, what's cosine squared over sine squared? Cosine. So do we know what cosine over sine is? Cotangent, and it's just squared. So, and 1 over sine squared. What's 1 over sine? Cosecant. So this is, I know, crazy, mind-blowing. I love this, right? Okay, so 1 plus cotangent squared theta is the same thing as cosecant squared theta. So if I see something where, if it was tangent or cotangent, I could solve it, but it's cosecant, like, hello, ways to manipulate it and change it, right? Or if I see a problem that involves cotangents on one side and they're asking me to make it look like a cosecant on the other side, I want to remember this identity. Now, hard part for you guys, all these identities are new, which means in a couple weeks when you have a test in front of you and you're trying to come up with the identities, you have to have like this scrolling list in your head of all the things you could put in for something, right? So that's your job, okay? So you might want to keep a running list of things that are useful to know as we go throughout the chapters, so that as we come up with more formulas, you start committing them to memory, and then right when you get that test, if you want to make yourself a big list or whatever, so that as you're going through, you can kind of manipulate and change what you want, but we're going to have to be familiar and know them, okay? All right, I'm going to take the same thing I just did, sine squared theta plus cosine squared theta equals 1. And I'm going to divide both sides of the equation by cosine squared instead of sine squared this time. Okay? So all right. So someone tell me what I get. Huh? All right, so these are called the Pythagorean identities because we saw very clearly that this first one literally comes from like the Pythagorean theorem on the unit circle, but instead of using x, y's, and r's, we just change those into sines and cosines, right? These other two are just a manipulation of this first one. So that means they all kind of originate from the Pythagorean theorem performed on that triangle, which is why they all get kind of clumped into this Pythagorean identity area. Okay? So 3 main formulas. You can rewrite these lots of different ways. Okay? We just did it with this one here to kind of make you aware so that when you see it, you now know that you could do that. Okay? Is this all right with everybody? Okay. So all of our problems in this section, everybody have all 3 written down? Any objections to me changing it? All of our problems in this section are going to focus on showing that a relationship is true, proving that a relationship is true, or simplifying. Like I said, basically manipulating things, okay? So this is one of our identities that we just came up with. If somebody said, show that this is true, it's basically like you're doing a proof, but maybe not the same exact style you did in geometry. So I don't want step and reason, but every step you do take should be justifiable, mathematically. You know what I'm saying? So you can't break any rules. You have to use things that are known to be true. So right now we can't just write like this is an identity. They basically want you to prove that this identity is true. Okay? Now, yes, you have to go step by step because basically the proof is your work. If I have questions, I'll ask you how you got from one step to another. I'll be perfectly honest with you guys. So upper division math, after you get past like calculus 3 and stuff, there's a couple of applied math classes, there's some linear algebra classes, but everything else, like abstract algebra, okay, analysis, are all these classes where you just prove like crazy things, okay? That's what you do. You prove. Your math homework, like page-long things of just like proving that something is true. Okay? That's what the upper division is. And so, just like you guys, I was a student of mathematics also, right? So if I'm sitting there and I got my midterm and I didn't know how to do something, but I knew like there was one step I couldn't get, but then what the rest like should look like after that, I just kind of skipped it and then like wrote the rest. And of course, like my teacher marked me down for stuff. So like I'll just kind of do the same thing for you guys. There might be things where you get like, oh, there's something that happens here that makes it this, and then from there it looks like this. And if that's true, and you're just missing that one step, you won't miss as many points as if you're like that can't be true. But I would ask you, like, okay, how do you know that? And if you can explain it to me, and you just didn't write it down, and I can see that clearly from your quick explanation of why that's obvious, then that's fine. If you can't explain it to me, then clearly it wasn't obvious. You just kind of knew it had to end up that way, but you didn't really know why, and those points would be taken off. Does that make sense, Matt? Is that okay? Okay. So be as thorough as you can. All right, so let's say that we had to prove that the 1 plus cotangent squared theta equals cosecant squared theta. Now, we know this is true because we took an identity, manipulated it, and made another one. But to prove this, what we basically have to do is take one side of this and work on it and work on it and work on it, manipulate it and change it without breaking any math rules or putting in things that aren't equal till it looks like the other side. Okay? So any ideas? First of all, which side do you guys want to work on? The left side or the right side? Okay. Yeah, so we're not going to use x's and y's, though. Instead, we're going to use things like sines and cosines. Okay? So Matt knows that cotangent has something he can plug in for cotangent. I'm with Matt as far as comfort level. I would like to start on the left side as well. Anybody have a good reason why they think I would want to start on? I'm not saying it's wrong. You can actually start on both, but I have a logical reason why I want to start on the left side.
Because in the cotangent, like you have cosine and sine, whereas in the cosecant you just have sine, so it gives you more to work with.
Good. Okay, so in the cotangent you have a cosine and a sine, so you have more stuff that you can like manipulate and work with. And notice that the cotangent's being added to 1, and you can like rewrite 1 however you want. And so you have two things that you could rewrite as fractions and like combine them together into one thing, right? So I usually like to start where there's more and try to combine it together with common denominators and stuff like that to get it to look like the other one. You'd have to be like pretty good at this to take the right side and turn it into the left side, because you're going to have to like put extra stuff in that's just the right stuff that makes it turn into the other side, because it's so simple already on that side. You would basically be expanding it out. So I like to start with like the larger, more expanded out thing and simplify it, because that usually helps me. So that's a helpful hint if you're not sure about where to start. Oftentimes both sides are equally ridiculous, and you could just like start on either one. But in this case, like the secant or the cosecant's pretty simple, and so I don't know, like I would have to really think about what to put in there, and it would be more difficult. So I'm going to start, like Matt said, like Julia said, I'm going to start on this 1 plus cotangent squared, and the first thing I'm going to do is I am going to rewrite the cotangent as cosine squared theta over sine squared theta. And you guys can do this. I'm just going to put an equal sign like that. When I'm working on one side of an equation, I want to prove it's equal. I don't have to keep writing that other side. You guys can do the same thing, as long as I know which side your equal sign's on, so I know which side you're working with, okay? All right, now, we want to take these two things, and we want to combine them into one thing. Notice that the right side is one thing. So like we did at the beginning, how I gave you that review problem, like 1 plus 3 over x. So you like rewrote 1 in a way that it could be combined with that fraction. How do we want to rewrite this one right here? Huh? Yeah, I want it to have the same denominator as the thing that I'm trying to combine it with. So one denominator means that denominator can be written itself with the numerator being these two things added together. All right, and what do we recognize? I see Helen, but I've said her name like 10 times already today. What do you recognize here? Now, you can't use that identity. That doesn't mean you can't use the other ones that we started with. So there should be something up here that you recognize. So I see Julia, Matt, and Helen, but I've M and Chow, but I've called on all of them today already. Alex?
Sine squared theta plus cosine squared theta is 1.
Good. Perfect. So sine squared theta plus cosine squared theta, if you look back, that's equal to 1. So this is the same as 1 over sine squared theta. And 1 over sine squared theta is cosecant squared theta. So I've done my proof or my verification that those two things are true. So similarities to geometry proofs. You know the beginning and you know the ending because the ending's already on the other side. And you need to take a logical sequence of steps that somebody could follow to get there. Difference, you don't write next to it like, this is the Pythagorean theorem. This is the, okay? All right? But somebody should be able to follow. So my thing is, if there's something from here, like say you went from here to here, I'd be like, yeah. But you might do that because in desperation, if you don't know what comes next, but you know where you're supposed to get, I've done it, okay? Let's be honest. All right? That you might just write this, and then you're like, I don't know, this. But maybe somebody wrote this and is like, yeah, that's 1, and that's the cosecant, and they wrote this. So that's where sometimes I'm going to have to ask you for a little clarification on what you did, okay? Is everybody okay with this idea of what we're doing here? Okay. Now that we're not proving that identity, we can actually use whichever ones. Now, A and B are the same. Good job, Ms. Stahl, right? So you're going to cross out B, okay? Because it would be the same as A. Or you can do it again after we do A if you really want to. All right, so I have sine theta times cotangent theta equals cosine theta, and I'm supposed to verify that this is true. So let's pick a side. Let's start manipulating and see if we can get it to look like the other side. So where do you guys want to start? Left side, right side? Left? Got more stuff to work with over there? Yeah, that's what I feel like too. See how it would be hard to start, like, what do I do with cosine? Now, I can do something. I can multiply that side by something as long as it's worth 1, which means it would just have to have the same numerator and denominator. But I'd really have to look at the other side to really think about what that's going to be. Whereas if I start on the left side, there's some immediate things I could do. What do you feel like you would immediately do when you see what you have on the left side? Raven? Good. Okay, so we're going to just rewrite cotangent as cosine theta over sine theta. All right, so then what happens? All right, Michelle. Good. Okay, numerator, denominator cancel each other out, so I'm left with cosine theta. That is exactly what it said on the other side. I am done. Okay. Now, sometimes, is it a good wow or bad wow? It's a good wow? Okay. Now, sometimes they'll say, like, can I work on both sides? And technically, the answer to that is yes. But in here, I'm going to be strict and mean and whatever you want to call it. And I'm going to make you work all on one side to show me how it equals the other side. But there is a very good reason for why I'm doing that. I let my class one year work on both sides. And the problem is, you can technically, if you understand what you're really doing, you can work on both sides. And then once you get to where they match, you can just take all the steps over here and do them in reverse order over here until they get what you want. So if you know what you're doing, it's not going to matter. My problem was people didn't know what they were doing, so when they were working on both sides, they were like, oh, I'm going to multiply both sides by 10. And I'm like, no. You're not allowed to pretend that they're already equal. You're supposed to show me that they equal each other. Multiplying both sides by 10 or something is saying, I already know they're equal and they stay equal when I multiply them by 10. Like, not okay. You can't multiply both sides by something or divide. You got to work. So that's why I limit you guys to work on one side. So you're actually doing a proof and not just assuming what you're supposed to be showing me is true is already true. Okay? Yes?
Could you also solve that problem by dividing by
No, because that's what, okay, so if you divided both sides by sine, you're assuming that this is a true equation, and you're starting to solve the equation, like dividing both sides by something like that. If you're supposed to be verifying the identity, you're supposed to be proving to me that it's true, so you can't use those properties that we use to solve equations, because we use those properties because an equation means it's true. We're using these things to solve it because the properties say I can do these things to both sides and it stays true. But that means you're assuming it's true, which we kind of know it is, but you're supposed to be proving that that's the absolute truth. So that's why we work on one side, and we don't divide both sides by something or multiply both sides by something. Okay? All right. Let's try some more. All right. Oh, Helen sees right away. All right, Helen, what do you see? Good. Okay, so this is where knowing our identity, see how important it's going to be, right? If you didn't have the sheet right there with you right now, okay? So 1 minus cosine squared theta, she sees right away that that's sine squared theta. All right, so I'm going to change that to sine squared theta. Okay. Then what happens, Julia? Good. And there's still 1 power of sine there left. So the cool thing about this is really complicated things, or things that appear to us to be very complicated, are actually not that complicated. The really good skill, whether you're going to spend your life verifying that trig identities are true or not, the good skill here is the problem-solving critical thinking skill, because your mind is really working on where the connections are and what you're going to see. I love them because I love puzzles. And so I feel like it's totally a puzzle. Like, oh, I'm going to try this. Like, I bet I can get it. And I feel like someone's trying to trick me. And then, like, I'm going to figure it out. I feel so great at the end. Okay. So, I know. You know, after weird people call me, that's what I do to make myself feel better. No, just kidding. All right. So, in part D, okay, where do you guys want to start? Left side or right side? Left side. We got more stuff we can, like, yeah, on the right side, I have to, like, put a lot of new stuff in that side, right? Because it's so simple already. So maybe I'll start on the left side. Okay, so I have sine squared theta times secant theta plus cosine theta. All right. Okay, so tell me what you guys want me to do first. Matt. I don't know. All right, that's okay. Raven. Okay, so let's just start with changing the secant to 1 over cosine and seeing if that helps us. So remember, I don't know if I said this in your guys' class or the other class, but when I was saying like what we were going to do next, I said I'm basically not going to help you unless you come to me with a paper where things have been scratched out, erased, right? And you have this like frustration, okay? Because if you just come to me with each problem you don't know how to do, like, oh, Miss Dahl, I don't know how to do this one. Yeah, I'm going to have to sit here and figure it out too, because these problems aren't like, well, you always use the quadratic form? Like, no. Okay? You have to sit there and try things, see if they work, see if they take you the right direction or the wrong direction, and then adjust. Okay? So let's see if this is helpful or not. All right, so that's going to give us a fraction over here. Okay? So sine squared theta over cosine theta. I don't think fractions are a bad thing in this sense, because this could actually be good. Because notice that on the right side, how many terms are there? 1. So basically, this is all supposed to get packaged together all nicely, which means there's got to be some way to combine these. So this actually looks like a good move, because see how this one has a denominator and right now this one doesn't? So hopefully I'll then be able to combine them together and get somewhere. Matt?
Could you do sine squared theta plus 1
Sine squared theta plus 1 over cosine theta. You mean to substitute for for this? Yeah. So first, I think that you already took one. So did you already think about this as like a fraction? Okay. So to combine these two together, though, they're going to have a common denominator. And the only reason I'm focusing on that is because we already said that eventually these should combine together, because on the other side, there is just one term, which means this all should combine together. And if it's going to combine together, these have to become 1, and they can't become 1 if this one has one denominator and the other doesn't have the same. Okay? So, Julia. Good. So I'm multiplying that by cosine theta over cosine theta. Totally allowed to do that because cosine theta over cosine theta is really just 1. Can I multiply stuff by 1 without changing it? Yeah. Okay. So this gives me sine squared theta over cosine squared theta. Oh, yeah, over cosine, sorry. Cosine squared theta over cosine theta. And now that they have the common denominator, I'm going to write them as one thing. All right, was that helpful? All right, Matt.
Now, sine squared theta plus cosine squared theta is what?
Good. So this is 1 over cosine theta, and 1 over cosine is really just secant. Craziness. Okay?